For 20 years, the story of the data center has been the story of layers stacking on top of each other, first corporate servers, then the cloud, then artificial intelligence. But right now, quietly, almost without most of the world noticing, a new layer is being poured into the foundation. And the people running the world's biggest data centers will tell you, quite plainly, that this one is genuinely different from everything that came before it. Walk into almost any major data center campus today, and you will find rows and rows of racks, humming fans, blinking lights, and an ocean of cables carrying information at the speed of light. For decades, that has been the picture of computing power. Bigger buildings, more servers, more electricity, more cooling. When cloud computing arrived, it filled these buildings with virtual machines. When artificial intelligence exploded, it filled them with graphics processors stacked wall to wall, drawing so much power that entire regional electrical grids had to be redesigned around them, each wave built on the one before it. Each wave asked for more space, more energy, and more heat management. But now, something fundamentally different is being wheeled into these same buildings. And it does not look, sound, or behave like anything that came before. It hums, yes, but underneath that hum is the rhythmic pulse of compressors forcing supercooled liquid helium through pipes, chilling a chip down to a temperature colder than deep space. It is quiet in places, eerily so, because the very thing that makes it powerful, the strange behavior of particles at the quantum level, can be destroyed by something as small as a passing vibration or a stray magnetic field. This is quantum computing, and it has officially left the laboratory. It is moving into the data center, and it is bringing with it a set of rules that nobody who built the internet ever had to think about. To understand why this matters, you have to understand what a data center actually is at its core. It is not just a building full of computers. It is an economic engine, a piece of real estate strategy, and increasingly a geopolitical asset. The largest operators in the world, companies that own hundreds of these facilities across dozens of countries, describe their growth over the last 2 decades as a layer cake. First came the corporations that needed to harden their own internal systems and move their operations off-site. Then came the telecommunications companies, wiring the world together. Then came the explosion of mobile apps, which needed servers close to users everywhere. Then came cloud computing, which turned data centers into the invisible backbone of nearly every business on the planet. And most recently, artificial intelligence arrived like a tidal wave, reshaping the entire industry around a single insatiable demand for computational power. Now, there's a new layer being added to that cake, and the executives who run these facilities are already preparing for it. They will tell you they cannot fully predict its size or its shape yet, because the technology itself is still evolving so quickly. But they are confident that it is coming, and they are confident that when it arrives at scale, it will reshape how data centers are designed, cooled, secured, and staffed. The numbers behind this shift are already staggering, even at this early stage. Market analysts tracking the quantum computing industry have put its current value somewhere between $1.5 billion and $3.5 billion, depending on exactly how you define the boundaries of the market. But almost every single one of those analysts agrees on the trajectory, upward and sharply. Some forecasts project the industry will multiply 5 or 6 times over by the end of this decade. Others, taking a longer view toward the mid-2030s, describe a market approaching $20 billion. And in the most ambitious projections, closer to $70 or even $90 billion once quantum technologies are fully woven into industries like pharmaceuticals, banking, and logistics. Government spending is accelerating right alongside private investment, with national programs in the United States, across Europe, and throughout Asia collectively planning tens of billions of dollars in public funding over the next several years, all aimed at building both the hardware itself and the workforce capable of operating it. So what exactly is quantum computing, and why does it require an entirely different kind of home? Traditional computers, the ones inside your phone, your laptop, and every server in every data center on Earth, operate using bits. A bit is the smallest unit of information, and it can only exist in one of 2 states, a 0 or a 1. Every photograph you have ever taken, every email you have ever sent, every video you have ever streamed, has been translated at some point into an enormous sequence of these zeros and ones. It is an elegant system, and it has powered 70 years of technological progress. Quantum computers throw that elegant simplicity out the window and replace it with something almost impossible for the human brain to intuitively grasp. Instead of bits, they use quantum bits, or qubits. And where a bit must be either a 0 or a 1, a qubit can exist in a blend of both states at the same time, a phenomenon known as superposition. Imagine flipping a coin. While it is spinning in the air, it is not simply heads or tails. It is both possibilities simultaneously, a blur of potential outcomes that only resolves the instant it lands. A qubit behaves something like that spinning coin, holding multiple possibilities open at once, right up until the moment it is measured. Now add a second strange property, entanglement. When qubits become entangled, the state of one instantly influences the state of another, no matter how far apart they are physically separated. Change one, and the other responds immediately, as if some invisible thread connects them across space. Albert Einstein famously distrusted this phenomenon, calling it spooky action at a distance, and yet decades of experiments have confirmed that it is real, measurable, and now, remarkably, something engineers are learning to harness for computation. Put superposition and entanglement together, and you get a machine that does not just process information faster than a classical computer, it processes it in a fundamentally different way. For certain types of problems involving massive numbers of variables and possible outcomes, a quantum computer can explore many solutions simultaneously instead of checking them one after another. This is why analysts at major financial institutions have described quantum machines solving certain problems in a couple of minutes that would otherwise take a classical supercomputer roughly 10,000 years to complete, a gap so enormous that it is genuinely difficult for the human mind to hold onto its full scale. That is not a typo, and it is not marketing exaggeration. It is the kind of leap that happens perhaps once in a generation of computing, and it is why some of the world's largest technology companies, along with the operators of the buildings that house our digital infrastructure, are paying very close attention. But here's the twist that makes this story so interesting for the data center industry specifically. A quantum computer is an incredibly fragile, temperamental piece of machinery. Superconducting qubits, the type currently favored by companies like Google and IBM, only function properly when cooled to a fraction of a degree above absolute zero, colder than the vacuum of outer space. Achieving that requires dilution refrigerators, enormous specialized cooling systems that look nothing like the air conditioning units cooling a typical server room. These refrigerators use rare and expensive substances, including helium-3, to reach and maintain those extreme temperatures. On top of the cooling challenge, quantum systems are extraordinarily sensitive to their environment. A vibration from a nearby hallway, the electromagnetic field generated by ordinary electrical equipment, even subtle fluctuations in temperature, can be enough to collapse the delicate quantum state the machine depends on, a process scientists call decoherence. When that happens, the calculation is ruined. So these machines cannot simply be bolted into a standard server rack alongside a wall of graphics processors. They need vibration-dampened foundations, carefully isolated from foot traffic and mechanical equipment. They need specialized shielding, sometimes described as a kind of Faraday cage, to block out stray electromagnetic interference. And because they are usually taller and more oddly shaped than conventional server racks, with helium and nitrogen piping running beneath raised floors, they often require modified physical layouts that look nothing like a typical data hall. Engineers who have toured working quantum data centers in Germany describe walking into facilities that feel almost like an entirely different industry, hiding inside a familiar shell. There is still the constant hum of fans in the background, the noise every technician associates with a server room. But layered on top of it is a new sound, a deep, rhythmic pumping, closer to the sound of a steam engine than to anything electronic, as compressors force supercooled liquids through the system to keep the atoms on the chip locked into their quantum state. In some of these facilities, the classical computing infrastructure sitting one floor below still consumes far more electricity than the quantum hardware above it, which tells you something important. This technology, for now, is being layered gently on top of existing infrastructure, not replacing it wholesale. And that idea, layering rather than replacing, is the key to understanding where this entire industry is actually heading. For years, the public conversation around quantum computing tended toward two extremes. Either it was going to change absolutely everything overnight, cracking every encryption system on the planet and rendering classical computers obsolete, or it was permanently 20 years away from being useful, forever trapped in university laboratories. The reality unfolding right now in commercial data centers is far more interesting than either extreme and far more grounded. The emerging model is hybrid computing. Picture a single data center campus that houses three distinct types of processors working in concert. Classical central processing units handle the everyday logic and coordination tasks they have always handled. Graphics processing units, the same chips powering the artificial intelligence boom, handle massive parallel calculations for machine learning. And now a quantum processing unit sits alongside them, called upon specifically for the narrow category of problems where quantum mechanics offers a genuine advantage. One senior executive overseeing quantum strategy at a major technology company described this future plainly. Engineers are no longer thinking of the quantum processor as a standalone curiosity sitting off in its own isolated lab. They are actively designing systems where a quantum accelerator sits physically close to a high-performance classical computer, exchanging information back and forth at high speed, each system handling the part of the problem it is best suited for. Even the company that arguably owns the artificial intelligence boom is now positioning itself at the center of this new hybrid future. NVIDIA, whose graphics processors are the beating heart of nearly every major AI data center on the planet, recently released a family of open-source software models built specifically to manage the errors that plague quantum hardware, part of a broader platform the company describes as quantum GPU supercomputing. The company is also pushing a software layer that allows quantum processors and graphics processors to be programmed together almost as if they were a single unified machine rather than two completely separate categories of hardware bolted together as an afterthought. When the company that built its empire on classical parallel processing starts investing seriously in making quantum hardware talk fluently to its own chips, that is a signal the rest of the industry tends to take very seriously. This hybrid approach is already happening in the real world, not just in theory. At one of Japan's leading research institutes, a quantum computer now sits right next to one of the most powerful classical supercomputers on the planet, working together on complex molecular simulations, handing pieces of the calculation back and forth between the two machines, depending on which one is better equipped to solve that particular piece. In New York City, a major data center operator partnered with a quantum computing company to launch a facility that combines quantum hardware with the same advanced graphics processors used for artificial intelligence, creating what the industry is now calling a quantum AI data center. In the American Midwest, a data center in Indiana recently became home to a new quantum optimization machine offered to businesses on a subscription basis over a dedicated quantum-secured fiber network, essentially quantum computing as a service, available on demand, the same way cloud computing transformed access to classical computing power over the past 15 years. That phrase, quantum computing as a service, might end up being one of the most important concepts in this entire transformation, just as most companies never built their own private data centers and instead rented computing power from providers like the major cloud platforms. Most businesses will likely never own a quantum computer of their own. Instead, they will access quantum capability the same way they access cloud storage or streaming video today, through a service hosted somewhere in a specialized facility, delivered to them over the internet whenever they need it. This model dramatically lowers the barrier to entry. A pharmaceutical company does not need to build a cryogenic laboratory to run a molecular simulation. A financial institution does not need to hire an army of quantum physicists to optimize a trading algorithm. They simply connect to a provider, submit their problem, and receive results, while the extraordinarily complex infrastructure required to actually run the calculation lies somewhere else entirely, professionally managed, inside a purpose-built facility. So who is actually using this technology right now, today, for real commercial purposes, rather than pure research? The answers might surprise you, because they are not exotic use cases pulled from science fiction. They are extremely practical, high-value business problems. One major global bank has publicly stated that using quantum computing techniques improved its predictions of whether a bond trade would execute at its quoted price by roughly a third compared to its previous methods, a meaningful edge in an industry where fractions of a percentage point translate into enormous sums of money. Financial services firms, more broadly, are exploring quantum computing for portfolio optimization, fraud detection, and risk analysis, all problems that involve searching through an almost unimaginable number of possible combinations to find the best outcome, exactly the kind of challenge where quantum's ability to explore many possibilities simultaneously provides a genuine advantage over classical brute force computation. Pharmaceutical and biotechnology companies represent another major area of early adoption, and for good reason. Developing a new drug traditionally takes 10 to 15 years and it can cost well over $2 billion, with a success rate under 10%. Much of that time and expense comes from simulating how molecules interact with each other, a problem that scales in complexity so dramatically that classical computers eventually run out of practical ways to model it accurately. Quantum computers are naturally suited to simulating quantum systems, which is essentially what molecules are, made of particles obeying quantum mechanical rules. Researchers believe this could meaningfully shorten the early stages of drug discovery, helping identify promising compounds faster and potentially bringing life-saving treatments to patients sooner. Logistics and supply chain companies are exploring quantum computing for route optimization and scheduling, problems that sound simple on the surface but explode into billions of possible combinations once you factor in real-world variables like traffic, weather, fuel costs, and delivery windows across a global network. And of course, there is the cybersecurity angle, which cuts in two very different directions at once. On one hand, quantum computing promises entirely new forms of secure communication, using the strange properties of quantum mechanics itself to detect any attempt at eavesdropping. On the other hand, a sufficiently powerful quantum computer could theoretically break many of the encryption systems that currently protect the internet, from your online banking to government communications. This is not a distant theoretical concern to the people who manage global digital infrastructure. It is a driving force behind an entire new category of technology called post-quantum cryptography. encryption methods specifically designed to remain secure even against a future quantum computer. Enterprise data centers are already being told that quantum-safe protocols will need to be standard practice well before the end of this decade. Not because quantum computers capable of breaking current encryption definitely exist yet, but because the migration itself takes years and nobody wants to be caught unprepared when that moment arrives. Now, let's talk honestly about the scale of what is happening today, because there's a meaningful difference between excitement and reality, and the most credible voices in this industry are careful to separate the two. As of right now, quantum computing hardware has only been deployed in a couple dozen data centers worldwide. That is a tiny fraction of the millions of data center facilities operating across the globe. Industry analysts studying this space describe quantum computing as being roughly where artificial intelligence was many years before its current explosive growth, a technology moving quickly, generating enormous investment and enthusiasm, but still working through fundamental engineering challenges before it becomes a mainstream part of everyday business infrastructure. One of the biggest of those challenges is error correction. Qubits are inherently unstable. They are prone to what scientists call decoherence, essentially losing their delicate quantum state due to any interference from their environment, whether that is heat, vibration, or electromagnetic noise. Building a quantum computer that can reliably perform useful, complex calculations requires an enormous number of physical qubits, dedicated purely to detecting and correcting these errors in real time, on top of the qubits actually doing the calculation. This is often described as the difference between noisy, intermediate-scale quantum computers, which exist today and can already tackle certain narrow problems, and fully fault-tolerant quantum computers, which most experts in the field believe are still several years away from commercial reality, with many serious estimates pointing toward the end of this decade, or in some cases, well into the next one. There is also a resource question that does not get nearly enough attention in the public conversation. Quantum computers may eventually offer significant energy savings for certain narrow categories of problems compared to classical brute force computation. But scaling quantum computing up to a truly large, fault-tolerant, commercially transformative level will require substantial amounts of electricity, water for cooling, and rare physical materials, including helium-3, a substance that is genuinely scarce and difficult to source in large quantities. Researchers studying this question, including scientists at a major United States national laboratory, have pointed out that most national quantum strategies around the world have not yet seriously grappled with these resource demands. As this industry scales from a couple dozen experimental installations to potentially hundreds or thousands of commercial deployments, the question of where all that helium, water, and electricity comes from will become an increasingly important part of the conversation, right alongside the more exciting questions about computational breakthroughs. There's also a very human bottleneck standing in the way of rapid expansion, and it might be the most underestimated challenge of all. Quantum computing requires an entirely different kind of expertise than traditional information technology. It blends deep knowledge of quantum mechanics with specialized engineering skills in cryogenics, precision fabrication, and highly specialized software development. The people who genuinely understand how to build, operate, and maintain this equipment are still relatively rare, and demand for that expertise is already outpacing the supply. Data center operators preparing for this next wave are having to invest heavily in training programs and actively recruit talent from a very small global pool of specialists, essentially building an entirely new profession from scratch, at the exact moment the industry needs it most. Universities are racing to keep pace with that demand, expanding quantum engineering programs, opening new research centers, and partnering directly with the technology companies building this hardware. But the pipeline of qualified graduates remains narrow compared to the scale of ambition being poured into the industry. Some of the very same institutions long associated with breakthroughs in classical computing, physics, and engineering are now standing up entirely new departments dedicated purely to quantum information science, training a generation of engineers who will spend their careers moving fluidly between physics textbooks and server room blueprints, a combination that essentially did not exist as a formal career path a decade ago. For data center operators, this means the competition is no longer only about square footage, power contracts, and fiber connectivity. It is increasingly about who can attract and retain the small number of people on the planet who genuinely understand how to keep a quantum processor stable, calibrated, and productive. So, what does the next several years actually look like, based on what the people building this technology are saying right now? Expect quantum computing to remain what industry insiders are calling a specialized demand layer for the next handful of years, adding pockets of highly customized infrastructure inside a small number of facilities around the world, rather than becoming a standard feature in every data center campus. Expect the hybrid model, quantum processors, working alongside classical processors and graphics processors, to become the dominant architecture, rather than quantum computers operating as isolated standalone systems. Expect quantum computing as a service to expand steadily, giving more businesses access to this capability without requiring them to build or maintain the extraordinarily specialized infrastructure themselves. Expect post-quantum cryptography to move from a niche technical concern into a mainstream business requirement, as organizations across finance, healthcare, and government begin the multi-year process of upgrading their security systems ahead of the eventual arrival of truly powerful code-breaking quantum machines. And expect the biggest technology companies in the world, along with the largest data center operators on the planet, to keep making increasingly public, increasingly confident bets on this technology, even while acknowledging that nobody can predict its exact trajectory with certainty. That combination, genuine excitement paired with genuine humility about how much remains unknown, might be the most honest way to describe where quantum computing stands today. It is not science fiction anymore. It is not a laboratory curiosity confined to university basements. It is real hardware, humming quietly inside real buildings, solving real problems for real companies right now, today. But it is also not yet the sweeping revolution that will make classical computers obsolete overnight. It is something more nuanced, more gradual, and in many ways more fascinating than either extreme, a new layer being carefully, deliberately added to the foundation of our digital world. One dilution refrigerator, one vibration, isolated rack, and one carefully engineered qubit at a time. The data centers of tomorrow will not look like the data centers of today. They will be quieter in some corners and stranger in others, filled with equipment that behaves according to rules discovered in physics laboratories rather than rules invented by computer engineers. They will require new skills, new safety protocols, new cooling systems, and an entirely new way of thinking about what a computer even is. And the companies that figure out how to build, staff, and operate these hybrid facilities first will likely hold a significant advantage in the next great era of computing. The same way the earliest cloud computing providers built an advantage that shaped the entire technology industry for the following 2 decades. Quantum computing is not simply revolutionizing data centers, it is quietly redefining what a data center is capable of becoming. And that transformation, patient, deliberate, and already well underway, is one of the most consequential technology stories unfolding anywhere in the world right now. Years from now, when people look back at this period, they may not remember a single dramatic headline or a single breakthrough announcement as the true turning point. Instead, they may point to exactly this moment, a quiet stretch of years when a couple of dozen unusual supercooled machines were carefully lowered into ordinary-looking buildings, when engineers who once worked exclusively in physics laboratories started wearing the same badges as data center technicians, and when the very definition of computing power quietly expanded to include something far stranger and far more powerful than anything built before it. The revolution will not announce itself with noise or spectacle. It will simply arrive, one dilution refrigerator at a time, until one day the strange becomes standard and the impossible becomes just another rack in the data hall.